Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I hope that everyone is having a very fine Thursday of this May 23rd, 2019. Thank you for joining me. Just want to be sure that everybody's able to hear me loud and clear before we get started. If you can hear loud and clear, then please give me a hands up on your side on the webinar. So I'm starting to see some hands going up. Sounds like people are able to hear me. That is excellent news. I want to let everyone know that this webinar is being recorded. That way, it'll be sent out to you later this week so you can listen to it again at your leisure. And then you can also send it around to your colleagues if they would be interested in listening in as well. And for those of you who are listening live, I've provided a PDF of my presentation. That way you can have it for reference later on. And then if you're listening in on the recording version right now, please email me directly at benkeyser@aft.com, and I'll be happy to send you a copy of my presentation. That's BENKEISER@aft.com. All right, just a couple of quick newsworthy items before we get started here today. I want to bring your attention to our website. If you were to go to our website, aft.com, you're going to see this wonderful little message right here that talks about how the brand new automated network sizing module for AFT Fathom, which is what we will be talking about today, is available, and we have a very special introductory price. And if you purchase the add-on module before October 31st, 2019, you'll be able to receive 50% off the add-on module. And that's a wonderful opportunity for you to be able to save some money on being able to work with an incredibly powerful capability that we're all really excited about here. If you are within the United States, you can go to the products menu and then you can view pricing information. And this is where you can find the pricing details for all of our software. And if you want to know what the ANS module for AFT Fathom is, then you can look on the AFT Fathom page right here. There is going to be a ANS module for AFT Arrow as well. It is very soon going to be officially released, hopefully within the next month or two. We are currently working on finishing up some documentation and testing. So stay tuned for our website and our newsletter, and you'll receive notice once the AFT Arrow ANS module is officially available. If you are not within the United States and you try to view pricing, it won't let you see it. And so if you're outside the United States, please contact one of your channel partners that is in your local area, and they'll be more than happy to get you the pricing information that you need for the new ANS module. And so that's where you can find those pieces of information. All right, getting into our webinar today, we're going to be talking about how to size your pipes in no time flat, how to use the automated network sizing module if you don't have any cost information. So before we get into that, these are our base products that we offer, and I'm sure that you're all familiar with them if you've listened to one of my webinars before. If you're not familiar with them, you can find information about all of our products on our website. Simply, again, go to aft.com, and then under products, just go to the AFT software overview. And this is where you can find an overview for each software tool that we have, and then you can learn more about each one individually. All right, so there are some helpful prerequisites to today's webinar, which obviously you're not going to be able to watch them before my live presentation right now, but I would recommend going back and watching these webinars when you have the chance down the road. Early on this year, I did a webinar on the top 10 features you can't go without. In that webinar, I talked a lot about how to use like the scenario manager, global editing capabilities. how to do multi pump configurations, a lot of different capabilities, which are, I also talked about importing piping component files, importing and exporting from Excel. There's a lot of really important capabilities and features that will dramatically increase your modeling efficiency and effectiveness. So be sure to check out that webinar. I also did a webinar on database management. There are some tips and tricks articles that I have written in the past which talk about how to use databases effectively. And the reason why that's important is because when you're dealing with the automated network sizing module, databases are a large part of that, as well as cost calculations. This is a webinar that I did a couple of months ago on how to do cost calculations within the software. And in that webinar, I demonstrated how to build cost databases from scratch. And so dealing with databases is very, very important in the context of using the new automated network sizing module. As far as ANS goes, we've already done 2 webinars on the ANS module, how to automate your pipe sizing calculations. This webinar was more of a background on what automated sizing is. I talked about the differences between design versus analysis and what a design tool is versus an analysis tool. And I demonstrated a very basic capability of what automated sizing looked like and why you would want to use the automated sizing capability. The next webinar was how to utilize the automated network sizing module for a more complicated system. The key thing about both of those webinars is that they were focused on using the ANS module with actual cost information, material and maintenance costs for pipes and fittings and pumps. And then I also included energy cost information. And for using the ANS module in terms of cost, monetary cost, you can size your system in 2 ways. You can size your system either to minimize the upfront initial costs, or you can size your system in order to maybe pay a little bit more upfront, but ultimately you'll be saving much more money in the long run with saving significant amounts of money in energy costs. So those 2 webinars talked about monetary cost with ANS. Today, I'm going to talk about how you can use the ANS module to automatically size your pipes when you don't have any cost information available at all. And that will help you very quickly size your pipes in no time flat. So today we're going to talk about how to size the piping system without cost information. I'm going to give you a background of the system I'm going to be sizing and kind of how that came from. And then I'll discuss the process on how to size the pipes, the pumps, and control valves without any information for cost. And what we're going to be doing is a non-monetary sizing process based upon the overall piping weight. So we'll go into that here in the next couple of minutes. Okay, a couple of months ago, back in February, I was fortunate enough to be able to publish an article for Pumps and Systems magazine, and that article is called Find the Right Pump with Flow Analysis Software. This is actually a link directly to that article. So if you're in the PDF and you click on that link, you'll be able to read the article. And I want to explain a little bit of the background on this particular system, because this is the system here that I'm going to be demonstrating today with the ANS module. So if you are familiar with our software and if you've worked through any of our walkthrough tutorials, this part of the system might be somewhat familiar to you. That is our, it's called our hot water system example. And if you were to go into AFT Fathom and open up the help file, then you'd be able to read about how to build that part of the system from scratch. So back in October and November of 2018, I did a 2-week road trip through the south of the United States, Tennessee, Georgia, Mississippi, Louisiana, met a lot of outstanding companies and was able to show our software to them and answer questions. And I met with several refineries and chemical companies, plants out there. And I heard a story from one of the senior engineers at one of the refineries I visited, and he talked about how they were recently putting 2 new heat exchangers online into their system for a relatively small expansion. And he asked if their senior management had done a flow analysis, and management said, no, we decided not to do a flow analysis. And sure enough, when they turned on the flows to the new heat exchangers, they didn't receive any flow at all because the pumps were already maxed out, serving the demands for the rest of the system. So the moral of the story is it's really important to do a flow analysis so that you can make sure that your system and your design will actually work. And that's what this article talks all about. So that'll give you some really good pointers on what you should consider when you're doing a flow analysis for your design. Now, the way that I came up with this system to imitate that story is I started off with our standard hot water system example model, and I slightly modified it to bump up some higher flow rates and whatnot. And then I built on the expansion part of the system right here. And so I had to do a lot of tweaking in order to get that model to work. And it was a really painful process because before using the ANS module, I would have to go in here and guess pipe sizes in different parts of the system and run the model to try and see if I was getting the flow rates and velocities and pressures that I wanted. And it was quite a difficult task. And then finally, once I got the system working for having a built model for the article, at that point I was done. But the thing is, that system that I created would have cost a certain amount of money. Now, if I would have had the time to go in here and try several different combinations of pipe sizes throughout the system, I might be able to find a combination of different pipe sizes that would be able to save money. So rather than using larger pipe sizes, I might have only needed to use some smaller ones here and there. And that's exactly what the automated network sizing module will do for you automatically. Is you're going to have various design requirements. Maybe you've got some flow requirements to the heat exchangers. You might have certain velocity requirements. Control valves have to be able to maintain good control. So you might have a minimum pressure drop across the control valves that you want to be able to achieve. Maybe you want to ensure that you have plenty of MPSH for the pumps. All are different design requirements that you have to consider when you're designing your system, and you want to make sure those requirements are met. And the ANS module will automatically meet your design requirements for you by figuring out what pipe size you need in order to minimize either your cost of your system or your overall piping weight. So that's the background of how I got to a system that simply worked. You know, it met the design requirements, but it very well may not have been the best design possible. So that's the background of how I'm going to be demonstrating today's model in our example. So again, make sure you do at least do a flow analysis to ensure that your system will work. For this example, I'm going to size my system with the expansion. That's one of the differences between the article model that I was using and the model today. In the article, the initial part of the system already existed and the expansion was not there yet. So if we back up a few bullet points here, this part of the system was already in use. It was already up and running and operating, and so that's where I was using Fathom to do a flow analysis to figure out what I needed for this expansion. The beauty of the ANS module is your goal is to try and save as much cost and improve reliability as best you can. And when you have the ability to do this from the beginning, you can automatically plan for expansions way ahead of time. That way, when you're going through and you're sizing your pumps based upon the expanded system being available. That way, you can ensure that you have the right size of pumps to meet your new flow demands when these new heat exchangers come online. The difference with what I'm doing today is I know that I'm going to have an expansion someday, so I'm going to design my entire system with the expansion in place, and I'm going to size my pumps as well as my pipes for the whole thing. That's really, really easy to do when you have a tool like the ANS module. So here's the process on how you would go about sizing the pumps, the pipes, and the valves. First, you would have to start with a pipe size guess. So there's a certain pipe diameter that I built in as a starting point, and then you would set up the ANS module sizing window to put together all of your design requirements and things like that. And then you'd be able to select your pumps once your pipes are sized. So the ANS module will go through and it'll select the appropriate pipe sizes. And based upon those new pipe sizes, then you'd be able to go in and get pump curves that will meet that operation. After that, you could do things like changing the pumps from fixed flow models, which were used for sizing, to an actual pump curve model. We can change pressure drop control valves to flow control valves. Then you can rerun the model without sizing to make sure that your design requirements are still met. And then you can also create a scenario to shut off the expansion part of the system. That way you'd figure out how many pumps you need in order to meet the flow requirements of just your two main heat exchangers that you have online. That way you can ensure that they're operating very close to the best efficiency point. And I'm going to cover all of these process steps today. Give me 1 second here. All right. At this point, I'm going to go ahead and switch over to AFT Fathom. So if you were to download the latest release of AFT Fathom, which was April 16th, 2019, you're going to see a new box right here in the startup window of AFT Fathom. And this is where you can be flagged for your intention to know where you can turn on the automated network sizing module when you have a license for it. And so this is a really helpful notification. That way you can find out more information on the ANS module. So I've already built my system, so I'm going to go ahead and browse to the model that I want to start with. So I just need to find where it is on my computer here. Okay, perfect. So now that the system is in place and I've already laid everything out, I'm going to go ahead and turn off the grid so it's a little bit easier to see. And I'm going to collapse my quick access panel. That way I have a little bit more real estate on the workspace. So this is the same system that was reflected in the Pump and Systems article. However, it is modified to be a better starting point for my ANS webinar today. So as you can see, all of the pipes here are using 10-inch diameter piping. That's not the real pipe size that I need. That is simply a guess or a starting point. So I've started off with 10-inch pipe diameters. Another thing is for each of my pumps, I don't have any pump curves yet. If you want to specify a pump curve, you can easily do so by clicking on this option right here for a centrifugal pump. However, I don't have a pump curve, so I'm going to have to do something different. And the way that I'm going to do that is I'm going to use the sizing option. So I turned on sizing. All you would do then is simply specify a fixed flow rate. So each of my pumps are going to be based upon a flow of 2,000 gallons per minute. So that's how I'm modeling each of my pumps. What I'm going to do is I'm going to use the ANS module to figure out what pipe sizes I need. Once I know my pipe sizes, I'm then going to transfer those new pipe sizes as new input for my system, and then I'm going to generate pump curves for each of these pumps, and I'll show you how to do that. Now, a caveat to when you're modeling your system like this, as you can see, I've got control valves here and control valves here, and those control valves are flow control valves. The reason why is because I need 1,400 gallons per minute through heat exchanger A and heat exchanger B. And then once the expansion comes online, I'm going to need an additional 1,300 gallons per minute through heat exchangers C and D. So after my system is sized, my control valves are going to ensure that I have the proper flow through each of those flow paths. But here's the thing. If you specify fixed flow rates for your pumps right here, as well as fixed flow rates for your control valves over here and here, what you have done is you have a flow or a known flow boundary right here, and then as you go around these two different loops, you have another known flow rate here, as well as a secondary known flow rate here. So this is an issue in mathematical modeling for anything that you're trying to solve, where you've got known flow rates for your boundary conditions. You can calculate a pressure drop in your system in order to meet those flow rates. However, what's the pressure right here, or the pressure here, or the pressure in this pipe right here? There's no way to know, because there's a number of multiple solutions that can exist which will be able to meet those flow rates. So this is where you have to have a reference pressure, which is completely outside of the scope with today's webinar. If you're not familiar with what I'm talking about, here's what I'm going to do. I'm going to give you a homework assignment. It's to go to the help file in AFT Fathom, and I want you to do a search for role of pressure. And if you do a search for the role of pressure, you're going to find this article called Role of Pressure, Detailed Discussion. And what it talks about is if you have a system with bounded flow rates here, you're not going to be able to mathematically calculate what's the unique pressure at each point in the pipe. And that's a major issue. So that's where you have to have a reference pressure. This article talks all about it. It's really important to have a good understanding of this topic, because it doesn't just come up when you're only modeling fixed flow rates. It can also happen when you are dealing with different combinations of pumps and control valves. So here we have several different control valves in different situations in the pumps model in different ways. You can very well encounter that same reference pressure issue in that fashion as well. So it's really important to fully understand that topic. So what I needed to do in order to, if I try to run my system right now, where this is a flow control valve at 1,400 gallons per minute, and this control valve is at 1,300 gallons per minute, here's what's going to happen. My system is not going to be able to be solved. If I try to run the model, you're going to see this reference pressure message. That's exactly what I was talking about. So click on help, read the help file, understand what that role of pressure topic is telling you about. It means that I've got a system with bounded flow rates and it can't solve the system. That's not a Fathom problem, that's a math problem. You wouldn't be able to solve the system by hand if you're doing it the same way by hand or with Excel either. So here's what I needed to do in order to get around this, is I needed to change a couple of these control valves to something different than a fixed flow rate. There's different ways around this. The way that I'm going to do it is I'm going to use, instead of a fixed flow rate, I'm going to use a constant pressure drop control valve. I'm going to set it to 10 psi. Why is that? Well, because for your control valves, you want to have a minimum pressure drop across the control valve. That way you can maintain good controllability for the lifetime of your control valve. So if your pressure loss from your fixed flow is really low, your control valve is not really doing anything. So I want a minimum of 10 psi. Why did I choose this one? Because it looks like this one is the hydraulically most remote control valve. So I want to ensure that this one definitely has the minimum pressure drop across it. So I put 10 psi here, and then I'm going to do the same thing with my other control valve on the expansion loop. This is going to be also a constant pressure loss of 10 psi. This is incidentally one of my design requirements. Minimum pressure drop across each control valve has to be less than, or it has to be at least 10 psi or more. So now if I run my model, it's going to converge. So here's what we're looking at when we are using 10-inch diameter piping with our fixed flow pumps. If I sort the velocity column by right-clicking on the column and then sorting in descending order, we can see here that we have some really high velocities based upon 10-inch diameter piping. One of my design requirements is that the velocities have to all be under 10 feet per second. Also, based upon 10-inch diameter piping, if you look at the pump performance, in order for each pump to get 2,000 gallons per minute, you're going to have a pump that can generate 360 feet of head and needs to be almost a 200 horsepower pump. That's a really, really big pump. Well, in my mind, it's big. May not be that big with what you're working on. If I look at the valve summary, we can see here that I'm getting the flows I need, at least a minimum of 1,400 in the A and B paths, and then a minimum of 1,300 in the C and D paths. And then we can also see what our control valve pressure drops are. So we've got violations in our future design requirements already. So this is where I'm going to use the ANS module to change the pipe sizes for me to get the appropriate design requirements that I need. So here's the process. Step number one, turn on the ANS module. How do you do it? Well, the first way is when you first run Fathom, you remember that startup window splash screen? That's one way that you could turn on the ANS module. Another way is if you go to the quick access panel on the right-hand side here, and you click on the box in the lower right-hand corner of the window right next to the status light. This is the other area where you could check the box for the ANS module to turn it on. Lastly, the third way is to go to the Tools menu, and when you go to the Tools menu, click on Activate Modules, and then simply check the box for ANS to turn it on. So I click OK. Once I turn on my ANS module, you're going to notice something that's a little bit different from usual. There's a sixth primary window here. These are all the same that were there before, but the sizing window is the new one. That's where you're going to do the whole sizing process for automatically sizing your system. So what I would do is click on sizing, and this is where you start. If you go to the sizing window, you're going to see that there's several panels down here at the bottom. These panels will walk you through the process on how to set up all of your different sizing parameters so you can automatically calculate your pipe sizes. You can define any of these panels in any order that you want, but it's easiest to go from left to right. It makes a lot of sense to do it that way, and it kind of progressively builds on itself. But if you need to go back and fix something, that's where you can go to any individual panel at any time. So the first thing that we need to do is we need to define a sizing objective. First of all, we need to determine if we're even going to try and size our pipes in the first place. If this is the very first time that you're running a particular model, you have the option to size your system, but you may not want to size it. If you choose this option, do not size, what's the purpose of that? Well, I'll show you. If I click on do not size, it's not going to size the system at all. It's simply going to run the model just like I was doing a regular Fathom run. So this is identical to not turning on the ANS module at all. I got the same results that I did before. So this is really good because you could start with your initial design or your initial pipe guesses, click on do not size, run your model, and just see where you're at with the results. And that will give you an indication of where you might need to start putting your design requirements in and whatnot. The second option is to calculate weight, but do not size. Well, the reason why that is useful is because what I might want to do is run my model with 10-inch diameter piping, and if I choose calculate the weight but do not size, what it's going to do is it's going to calculate the overall pipe weight, and I might want to know what that is. How much does the system weigh or cost based upon 10-inch diameter piping? Now, the next thing that you have to do is if you calculate weight and use that option, you do have to go to the sizing assignments. And I'm not going to talk about this in detail in this step, but I'm going to say include in weight. So what this is going to do is for all of these pipes, I have told them to calculate what the weight is of each pipe based upon 10 inches in diameter. So once I do that, I can run my model, should be able to run my model. Let's try this again. Pipe weight, minimize. Okay. Well, I wasn't expecting to see this, but I just found something that needs to be adjusted here. So ultimately, when you get the next maintenance release, this will be fixed here. This is telling me that I need to assign a cost database, but the thing is, I don't have a cost database. If I was doing monetary cost, I could size my system for material cost, installation cost, maintenance costs, energy cost, etc. And when you're using monetary cost for your sizing objective, then that's where cost databases are needed. In this case, if we're only doing piping weight right here, then cost databases are not needed. And so this should not be flagging my attention. So this is a issue that we need to fix. So here, if you were to calculate the weight, it will tell you how much your piping system costs based upon 10 inches in diameter. But what I want to do is I'm going to perform my sizing. So I want to actually change the pipe size of all of the pipes in the system. And when you don't have any cost information, you obviously cannot use monetary cost. So there's other options which makes the sizing really easy for you. You can size based upon the piping weight, the pipe and fluid weight. Maybe you have a really heavy fluid, which maybe it requires a really thick wall thickness perhaps. You can minimize flow volume or inner surface area, etc. So those are quick and easy methods of sizing your system when you don't have any cost information, and that's what I'm going to do today. So my objective is to minimize the piping weight, and the reason for that is because weight usually correlates really well with cost. If you have a smaller overall piping weight, your overall piping cost is going to be lower. So that's why we want to minimize piping weight. If we minimize piping weight, it's going to also be minimizing initial cost without having cost information built in. So this is the first step. Second step is to move on to the sizing assignments panel. So if I click on sizing assignments, here's what I have is a row of all of the pipes in my model, and this is what it's what it's going to look like when you first go to this panel is all the pipes would actually be set. This is the default way that it's going to look. All of your pipes are going to be in here where there's going to be no groups set up, and none of the pipes are going to be sized or calculated on their weight. So this is the same thing as just doing a standard Fathom run, no sizing, no cost calculation. So obviously we want to size the pipes. So what we would need to do is check the bubble or the buttons here to make sure that all of the pipes are included right here in the weight calculations to automatically size them. Now, why do I have this option to include in weight if size changes? Well, the reason why is because of the case where if I already have this existing system and the only system I'm trying to size is these pipes right here, there might be a couple other pipes in the original system I could size. So if I have the flexibility to maybe change these pipe sizes out and these pipe sizes while designing my expansion, then the option to include in sizing if it changes, that's where if there's a better pipe size that can be used, then that's where it'll change the pipe size for those pipes that are allowed to change. That's why I have the second option for include in weight if size changes. So if those pipe sizes in the original system, if they're not changing our pipe size, it's just going to it's not going to care about what their weight is or their cost. But if they change their size, then you want to know that information. Now there's a much easier way to get all these bubbles checked, and I'm going to show you that here. First, what you would do is I'm going to set these back to the original case, and nothing is initially selected. So if you click on all, that's going to select all of the pipes for you. If you go in here and click on this button to always include in weight, look at this. Voila! I have now moved all of my pipes over so that all of my pipes will be automatically changed, which is wonderful. That way I don't have to go through and click each button individually. Now here's the thing. If I do that and I do nothing else, I've got 35 pipes on my workspace. What this will do is it will use 35 variables where each pipe really could have its own different diameter, and none of the pipes would be the same, potentially. And that would potentially help you get a really, really good design, but it wouldn't make sense to have a different pipe size for each of these pipes or a different pipe size for each of these ones. So this is where you would need to size your pipes a little bit more intelligently rather than just sizing them all at a time. So here, as you can see, when I move all of my pipe sizes over, I've got 35 independent pipe sizes. So this is where we're going to talk about costs or common size groups. That's the pipe grouping over here. So what I'm going to do is I'm going to move my sizing panel or my sizing window over to the right. And then on the left-hand side, I'm docking my workspace. And this is going to make it very easy for me to create common size groups. That way, I can go in and have pipes be sized, which will be all the same diameter. So instead of having 35 individual pipe sizes, I want some more commonality. So here's what I'm going to do, is I'm going to start by creating a new common size group. So I'm going to click on this button right here. I'm going to click on new, and I'm going to create a common size group called main header pipes. So now that I have a common size group, the next thing I'm going to do is I'm going to select the appropriate pipes on the workspace that I want to throw into that group right here. So the next step is to go in and select those pipes. So that's going to be these 3 pipes and these 2 pipes. So I've got 5 pipes that are going to have the same diameter when they are sized. That's because I want to buy all my header piping in bulk, and I don't want a whole bunch of different pipe sizing. So I select the pipes on the workspace. After I select them on the workspace, I can click on the workspace button down here. And once I click on the workspace button, it will highlight the rows for each of those individual pipes. The next thing that I would do is click on Move To. I'm actually going to click on the arrow because I'm going to move these pipes over to my new common size group, main header. So this is now going to have these 5 pipes be all the same diameter in the end when they are sized. There are several other common size groups that I have, and I've got common size groups for my pump piping here. So I'm going to select these 3 pipes right here for pump A, and then I'm going to click on new, and this will be called pump A piping. And since they're selected on the workspace, I click workspace, I click on the little drop-down menu and then move them over to pump A piping, and that's all there is to it. Secondly is I'm going to select my 2 pipes for pump B, and then I'm going to create pump B piping. And so now I click on workspace, move to pump B piping, and that's all there is to it. Next, I've got the piping connected to pump C. So right here, I'll click on new, pump C piping, and then I'm going to click on workspace, move to pump C. And I'll just keep going through this whole process. The next pipes that I have in a common size group are going to be the pipes here in the heat exchanger A flow path. So when I click on new for new common size group, this will be called HXA piping. Again, I click workspace, move to HXA piping, and then I'm going to select these pipes right here. This is going to be HXB piping, and then workspace, move to HXB. If I scroll over, you'll be able to see how they're all in HXB piping's column. I've got a couple more common size groups. This right here is going to be the HXC piping. Click on workspace, move to HXC piping, and I'm going to do one more. And the last size group is going to be right here, and I'm going to click on new, and this will be called HXD piping. Click on workspace, move to HXD, and there they are. And so I've got those common size groups all set up. Now, something to look at is in my common size groups window, what I could do is I can sort by the pipes that are all in the same group. So rather than sizing my pipes sorting my pipes numerically, I can sort them by the common size groups. Now, the reason why I want to point that out is because it makes it easier to see which pipes are in which groups. But look down here. There are several pipes that are in the not in group column. What's going on with that? Well, let's take a look at some of those pipes. I've got pipe 5 and pipe 8. Let's see where those are in the model. If I scroll over here in the model, pipe 5 is right here and pipe 8 is right here. Well, those 2 pipes are going to be carrying additional flow than the individual piping to each of the pumps because they have more flow in them. So those are not going to be the same pipe size as the A, B, or C pipes. So I have left these 2 pipes to not be in any group. They may or may not be the same size. If I leave them in their own not in group by themselves, they could have different diameters, but they might also have the same diameters, just by the way the math works out. And then also I have my secondary header pipes, which would be this pipe that leads to the expansion loop, and then this pipe right here that ties back in, followed by that pipe. So those are pipes that I'm going to let change individually. So that's why they're not a part of any common size group. All the rest of them, when the ANS module is going to change their pipe size, each of these are going to be the same diameter. So all of the pipes in this common size group right here, they're going to be the same diameter. Why is it important to do this? Well, you want to have some commonality. That way, you're not having to get a different pipe for every single pipe in your system. But there's areas where it'll make sense to have the same piping. For example, in this flow path here, you'd probably want to have the same diameter, same idea for this flow path. But the other reason is it makes the solving process better. As you can see, when I created those common size groups, I went from 35 independent variables, which would change all 35 pipes independently of each other, down to 14. So that's going to make it a lot easier to be able to size the system here with a smaller number of variables. So now that I've created all my common size groups, this process is completed. The next thing is to move on to the candidate sets. So if I click on the candidate sets panel, here's what I see, is this panel here. What candidate sets are is for each of these different pipes, they're going to result in a certain size. Also, they're going to result in a certain material and schedule. Well, the thing is, when the ANS module is trying to figure out which pipe size that it needs, you have to specify a group of materials and a group of sizes that are eligible to be used for that piping in your system. So if you're only able to use HDPE pipe, then you'd want to make sure that you put in a database for HDPE. That way it uses HDPE piping. In my particular case, I'm just going to use steel. And so what I'm going to do here is click on New, and I'm going to create a new candidate set. So I click on New, and I'm going to call this STD for standard steel pipe, steel ANSI pipe. And this is where you select which type of pipe that you want to work with. So there's all these different choices that are available. As you can see, there's gold piping available. This is piping if you're in the upper echelons of the business. This is actually a custom pipe material that I made up. It's not real, obviously. But the reason why I showed you that is because if there's a pipe material that we don't have available for you in our database, you can very easily create your own custom pipe material database, and that material will be available in this list. That's outside of the scope of this webinar. If you watched the previous webinar I did on databases, you'll see how I build a custom pipe material database. So what I'm going to do is I'm going to select steel ANSI. That's the pipe material that I want to use. And then there's different ways that you can sort your piping. You can sort it by standard. The standard way of sorting everything is by size. So I've got a certain size and then all the schedules within that size. Well, the thing is, you're potentially going to have different costs in the end for each different schedule because they're different wall thicknesses. So more commonly, what you would probably be doing is sorting by type or schedule or class, and then your sizes. Hang on one second. Excuse me. So here I want to use all of the pipe sizes within the standard class. So if I expand STD for standard, these are all the pipe sizes I can use, all the way up to 48 inches. So here I'm going to click on the STD expanded part here and click add, and that adds all of the sizes all at once, which is really nice. But I don't care about like an 8-inch or a 1/4 inch. So everything that's less than 1 inch, I'm going to delete. I'm not going to search, I'm not going to consider any pipes less than 1 inch in diameter. So once I click OK, I now have a new candidate set that I can use. So these are all of the potential sizes, or I'm sorry, these are all the potential sizes and types of steel pipe, and I'm going to specify what can be used for my different size groups here. So that's the next step. As you can see, it's red. That means I need to define it. So really, what you could do is you could have different pipe material for the pumps, different pipe material for the heat exchangers, different pipe material for the headers. And that's where you would have multiple candidate sets. That way you would if you had multiple candidate sets, you would see multiple columns, and you would just specify which candidate sets go with which pipes. Here in my model, everything is going to use the steel ANSI standard pipe set. So I just click on all, and then I make them all be assigned to standard steel pipe. And now I'm done. As you can see, once I'm finished, I have a little green check mark telling me that I'm done with each of those steps. Now, I don't have to define any design requirements. I could run my model right now. But if you don't put design requirements in, it's not going to fix the design to your best possibility. It's going to use any size that it needs for running your system. So that's where you want to put in some design requirements. So that's my next step, is design requirements. And I'm going to have a few different design requirements in my system. I want to ensure that the heat exchangers right here receive a minimum flow of 1,400 gallons per minute. Well, for design requirements, we need to do design requirements on the pipes themselves. So those pipes are going to be 1,400 gallons per minute minimum. These are going to be 1,300 gallons per minute minimum for those heat exchangers. So here's what I do is I click on New, and I give the design requirement a name. I'll call it HX, and B minimum flow. And then you would choose the parameter. So the parameter is volumetric flow rate, and the minimum flow is going to be 1,400 gallons per minute. Now this is where you have to specify which pipes or which common size groups that this design requirement applies to, because it wouldn't necessarily apply to all pipes in your entire system. So this is going to apply to HXA piping and HXB piping. If I click on the little expansion, you'll see the different pipes that are in each of these common size groups. So if you click on this one and this one right here, it then checks all of these boxes here for you. So that saves you several clicks, makes it nice and easy to use. Second design requirement is going to be HX, C, and D flow. So here, my volumetric flow rate is going to be my parameter. I need to use minimum, and it's going to be 1,300 gallons per minute this time. And that's going to apply to HX, C, and D piping. There's one more design requirement for pipes that I'm going to specify, and that's going to be a maximum velocity. 10 feet per second, max velocity. So I type in my name, I give it a parameter, which is velocity. Here it's going to be maximum. I don't want my velocities to be above 10 feet per second. And this is actually going to apply to all of the pipes in the entire system. So I'm checking the boxes for all the common size groups and all the pipes that are not in any groups. So that way, every pipe has to have a less than 10 feet per second velocity. One more design requirement that I mentioned is my control valves have to be able to maintain good control. So I want to specify a minimum pressure drop, or maybe a minimum open percentage, or a certain CV value that can be used for my control valves. That way they can maintain good control and not be failing on me all the time. So what I'm going to do is click on control valves right here. Let me circle where I clicked. I clicked on that button, and I'm going to click on new to create a new control valve design requirement. So this is called control valve minimum DP. So that's the name. I'm going to choose pressure drop as my parameter, and it's going to be a minimum pressure drop of 10 psi. Now the thing is, control valve B and control valve D are using constant pressure drops already, just so that the system can solve right now with these being fixed flow pumps. So because they're already using the minimum pressure drop, I don't have to specify design requirements for those two control valves. I only need to check the boxes for flow control valve A and flow control valve C. Once I have sized my pipes and then I find pump curves and I've changed my pumps to pump curves, I can then go back and change these two control valves to flow control. Then I can change these boxes here to make sure they're getting the minimum there. All right, my design requirements are all set up. Last thing is to pick a sizing method. Again, assigning cost databases is not needed because I'm not doing any cost calculations with this, or I'm not dealing with any cost size. It's all based upon pipe weight. So here I'm going to choose a sizing method. There's two options. There's continuous and discrete. Continuous is any internal hydraulic diameter. So you could end up with a final pipe size of 16.378 inches in diameter, and that's what it would need. Well, that would not necessarily be a standard pipe size that you could buy. So you want to make sure that when it's sizing your pipes that you do discrete sizing. That way it picks from a discrete list. The list that it's picking from is your candidate sets. When it selects a certain pipe size, it has to be exactly any of these diameters that can be used. So I'm going to choose discrete sizing, and then you would pick a search method. I'm going to use genetic algorithm, and I'm going to start with continuous. The reason why I'm starting with a continuous sizing is because it finds a better starting point. So right now, I've got 10 inches in diameter. So if I start with continuous, it will be able to find better pipe sizes based upon a continuous sizing process. Once that's done, it'll have a good starting point to then select the actual nominal size that I need. All right, so everything is all set up now. So I'm going to save the model and I'm going to go ahead and run it. And this shouldn't take too terribly long to run. One thing I want to mention is when you're using the ANS module, it will typically run longer and maybe even a lot longer than a regular Fathom run. A regular Fathom run is typically a couple seconds, maybe a few seconds at most. But what's going on here is Fathom is running the system based upon a certain pipe size. So if I move this out of the way, it's running my model based upon 10 inches in diameter, and it needs to get a hydraulic convergence first, just like it does normally. After it achieves convergence, it calculates to see if what the piping weight was. And when it calculates that piping weight, it checks to see if my design requirements are satisfied. If my design requirements are not satisfied, it then has to change pipe sizes in order to get design requirements that are met. Once design requirements are all satisfied, then I would have a feasible design. That means my design will give me the design requirements that I want. But then it starts changing the pipe sizes further in order to help me minimize the piping weight. So it might find certain pipe sizes that work, but there could be different pipe sizes that will actually work a lot better and will ultimately save you lots and lots of money in the long run. That's why you're using the ANS module here, because it's going to give you a very good, the best possible design, because look how many iterations this is doing. This has done tens of thousands of hydraulic runs. That's running Fathom, several, tens of thousands of times. And then it's changed the pipe size over 1,200 times in only a matter of 2 minutes in order to try and find the best possible design for me. Now, while this is still finishing up here, I think it's almost done running, there are different methods that you can use for doing your sizing process. A little caveat that I want to mention is when you start working with the ANS module, play around with these different methods and do your own little bit of a sensitivity analysis, because some methods work better than others. We are not the creators of the methods. We use the methods in our software. They were written by Vanderplaat's research, and they're optimization technology that has been around for 40 years, and it's very, very powerful technology. So the reason why I mention that is because there's different calculus-based methods that you can solve this system, and certain methods work better for different situations. If you go to our help file, we talk about different methods in more detail. That way you can learn which ones are better than others in different circumstances. But the thing is, if you use different solution methods, it could potentially result in a slightly different design. So if I'm using the genetic algorithm method, it will ultimately calculate certain pipe sizes for everything in the system, which would result in a certain piping weight. If I use one of the other methods, it might result in a different piping weight and a slightly different size that I might need. So when you're using this, play around with the different solution methods. Also, play around with your starting point. I've started with 10 inches in diameter. If you start with 10 inches in diameter, or 2 inches in diameter, or 20 inches in diameter, those could potentially affect the final solution. So it's important to play around with some different conditions. So you would be doing a little bit more analysis with the ANS module, where you don't want to just click on one and done. But ultimately, it's really going to save you more time, because no one has the time to go through 1,700 different choices of pipe size combinations. So now that I've got some results, let's look and see what's going on. So if I go to the output window, here's my answers. My cost report, I can see that my total pipe weight of the entire system is 241,000 pounds mass. Now here's the thing. This is only considering piping weight. As you notice, I have in here, I've got T's, I have elbows, I have heat exchangers, I have valves, I have pumps. There's no way to be able to determine what the weight is for any of those different components. So when you're doing a weight sizing process, it's piping weight only, but it's going to give you a very good first cut at your design when you do not have any monetary cost information yet. So once you determine your overall pipe sizes, down the road you'll get cost information. Then you could update your cost values and then refine your design a little bit further to get some better values. So here's what we have. As you can see, it's sized all of my pipes. If I click on the sizing tab right here, it will show me what the ultimate pipe sizes need to be. So you can see how the pipe sizes change all throughout the system. These are the different schedules that are needed, and these are the different hydraulic diameters for each nominal pipe size. Now let's take a look at design requirements. We want to make sure our design requirements are met. So here we've got our flow requirements through heat exchanger A and B, flow requirements through heat exchanger C and D, and then we have our velocity requirements. So as you can see, they're not set for every single pipe right here. These are exactly 1400 because I've got a control valve. So this flow is going to be a bit higher because I'm not controlling the flow rate through that path. Now, the reason why you see two different colors here, the blue is indicating that these velocities had a major impact on driving the design for selecting pipe sizes based upon the initial continuous sizing process. Once the continuous sizing process was done and then it was doing the discrete sizing, these didn't matter so much anymore in blue. The main pipes that drove the design for the discrete were these ones. That's why they're highlighted in yellow. If you read our documentation, I'll give you a background on what the different colors mean once you get using that. Now, here's the next step, is to pick pump sizes that will meet this operating condition. So here's what I would do next. If you hang with me, I'm almost done. I just got a couple more minutes here. So for my scenario manager, I'm going to create a new scenario I'm going to call it pump selection with sized pipes as input. So when I create that scenario here, you can see that the input is still based upon 10 inches in diameter. So what I need to do is I need to take the results of the pipe sizes that were calculated right here, and I need to transfer those to input. So what I'm going to do in this scenario, my child, is I'm going to click on the thumbtack. That's where you can transfer your resulting pipe sizes to input. So if I click on that, I'm going to transfer both the calculated pipe sizes and the results. Click OK. So now if I go back to the workspace, now you can see here, if I reload this scenario, look at that, the pipe sizes have changed. So here we've got 18-inch pipe, 14-inch, 12-inch, 8-inch, etc. So now all my pipe sizes that were calculated and automatically determined have now been applied as input. So now what I can do is go to the sizing panel. This is where I'm going to click on do not size, because I just want to rerun my model and I want to select pump curves. So I click on the run button. It's not going to size the system. It runs a lot faster. I can go to my output here and I can look at the results at a different level now. So here I can still go to my design requirements and ensure that all of my design requirements were met. And you can see what the overall resulting parameters are. You can see what your pump performance is. So remember when I was using 10-inch diameter pipe and I needed like 360 feet of head? That's not the case. I only need 120 feet of head and a 60 horsepower pump. So that's going to be a lot smaller than based upon 10 inches in diameter. If we go to the valve summary tab, you can see what the pressure drops are. So I've got my fixed flow here, and I've got my fixed pressure drops here. As you can see, all the control valves are above the minimum pressure drop of 10 psid. So now I'm going to select pump curves. So I go to click on this pump with a spark on it right here. This is going to use IntelliClip, which is an outstanding third-party company in Pennsylvania. And I'm going to use the internet to select a pump from a real vendor that will match that operating point. So this is the IntelliClip website, and these are the pump vendors that will list their online pump catalogs for free without requiring a subscription. IntelliClip works with over 30 vendors, so if you have subscriptions to other pump vendors, then you could get more access to more databases here. But this is what's available for free. So I would use Pentair just to start with, and I'm going to select a pump. So I'll click on next, and this is going to find me a pump that will work based upon my operating point. So here I'm going to sort everything by best efficiency point from highest out of proximity to the lowest. So the pump that I actually selected already was one of these two. So what I did was I clicked on that pump and it brings up the online spec sheet. You can download this entire spec sheet as a PDF by clicking on download, but what I need is this IQX file. The IQX file is what you need to bring into Fathom. I've already done that. So I go back here and I move on to step 2 and I open up my file, and that's going to be this file right here. And now I'm going to apply the pump data. I'm going to apply the pump data to each of these pumps in the model. So now when I go back to the workspace, if I open up each of these pumps, you can see that I've got my head curve, MPSH curve, and the efficiency curve. So now I've got much better realism in my model. I can then go back and change this control valve to a regular flow control, 1400 gallons per minute. And then I can change this one to 1300 gallons per minute. All right, so now I've got everything all set up. Again, when I'm doing my run, I'm not going to size it. So I'm just going to rerun the model and make sure all my design requirements are met. and it calculated the results. And so now if I go to pipe design requirements, I can see that all of my design requirements are still met. This time I'm getting exactly the flow I need through each heat exchanger flow path. The reason for that is because I'm fixing the flow rate with my control valves. So I've got 1400 and 1300. As you can see, the pressure loss through each of the heat exchangers, the pressure loss through each of the control valves is above that 10 PSI minimum DP. So these control valves are going to have good controllability. Then finally, if I go to my pump summary, I can see where my pumps are actually operating. So they're not actually operating at 2,000 gallons per minute, that around 1,800. And if I add on more pump parameters, I go to the output control window and I want to click on the pumps button. So I care about what my efficiency is. So I'm going to add the efficiency to this list of parameters. I want to see my percent of BEP. I want to see my BEP flow rate. And then I want to see my MPSHR. And I'm going to move my MPSH down and I'll add my MPSH margin. That way I can make sure everything is good. So here, when I added on those additional pump parameters, look at this. Even when using the control valves, my pumps, they're not operating at the 96% of the BEP as if they were at 2,000 gallons per minute, but they're operating very, very close to the BEP. So this is still really good. A lot better than 20% of the BEP. And then you can see how your MPSH compares. I don't have any MPSH issues. Last step that I'm going to do today is to create a third scenario with expansion loop off. So here, this is where I've sized my entire system. This is my design, including the expansion loops, and my pumps were sized based upon this expansion loop being here. But in the initial stages of production, the expansion loop, this is not available. So I'm going to turn everything here off. So there's no flow in that path here. So now I only have flow traveling through this circuit. Well, let's run the model and see what happens with that being the case. When I run this, what you're going to find is that the pumps are going to operate a lot differently for 1,400 gallons per minute through each heat exchanger. So here, look at this. Our BEP proximity is terrible, 45% of the BEP. Well, what do? We just designed the system. Do we need to redesign the system again? No. Here's what you would do is you would simply go in and try turning one of the pumps off. So I'm going to try turning off pump C. And I want to see if only running pumps A and B do a better job and meet their BEPs closer with the given system. So when I turn off pump C, what you're going to find is that pumps A and B are actually going to operate a lot closer to the best efficiency point. So we look at the pump summary here, they're operating now at about 68% of the BEP. It's not 86 like it was before, but it's a lot better than 40%. So the next thing that you could do is you could do another scenario where you try changing your pump speed. And so with pump A and B, instead of running these two pumps at 100%, I might try running them at maybe 87% speed. If I run them at 87% speed, I might get a little bit closer to my best efficiency point. So let's see what happens. This is the last thing I'm going to run today. So this will converge nice and quickly here. Let's take a look at my pump operation. As we can see for our pumps, I'm operating at 87% speed, and look at that, it brought it up to just under 80%. So this is where your analysis with Fathom comes in really helpful, is you can still make sure that you're meeting all of your design requirements for your original system when the expansion loop is not built yet. So when you don't have the ANS module, it's a lot more difficult to guess and check the pipe size of this system, and it makes it really hard to really know if you've got the best design possible. And if you have the ANS module, it's going to save you massive amounts of time. It'll ensure that you have a really good design, and it's so that you can make sure that you have a better way of planning for expansions in the future up front on your initial design basis. That way you can select your pumps appropriately so that when you turn on this expansion loop, it actually works and your pumps actually operate reliably like they should. Thank you all very much for your time today. I really appreciate you listening in. If any of you want to try out the new automated network sizing module for AFT Fathom, contact your channel partner or feel free to contact me and we'll be happy to get you set up with that. Take care, everyone. Have a wonderful rest of your week.